So greeting to Dr. Ang. Today we would like to present our group assignment 2 with title Mean Value Theorem and its application improving theorem to solve discrete dynamical system. We are from group 1. I am YIING, the leader, and my member are DESMOND, CHING, YIING, CHEONG, and CHING. So the presentation will cover introduction, problem statement, methodology, examples, and solution, and then conclusion.
My name is CHEONG and I am the next presenter. I am going to present about the introduction of mean value theorem. Mean value theorem is formulated by mathematician Augustin Louis Cauchy, which lived from 1789 to 1857. Mean value theorem is a fundamental concept in calculus which establishes a relationship between the derivative of a function and its average rate of change. Mean value theorem has broad application across various disciplines. It provides valuable insights into function behavior and analysis. Mean value theorem states that if a function f of x is continuous in a closed interval a to b and is differentiable between the interval, then there exists at least one point, which denoted as c, and it is in the interval a to b, where the derivative is the average rate of change over closed interval a to b. In mathematical notation, it is written as f prime c equal to fb minus fa over b minus a. There are two conditions for mean value theorem. The first condition is continuous, which means the function f of x must be continuous between the interval a to b. In layman terms, it indicates the absence of jumps, hole, or vertical asymptotes within that interval. The second condition for mean value theorem is differentiability. F of x must be differentiable, and the derivative exists and is well defined at each point within the interval.
Greeting everyone, my name is Lebian. So I will explain on the application of the mean value theorem. So the first application is determining instantaneous rate of change. So the mean value theorem guarantees the existence of at least one point where the instantaneous rate of change match the average rate of change. And it can analyze the function behavior and identify minimum and maximum points of rate of change. And then the next application is solving optimization problem. So mean value theorem can identify critical points and determine the corresponding minimum or maximum values. And it is essential in optimization in finding optimal values for various parameters. And then it also can be used in the estimating of the value. So mean value theorem allows for estimation of function values by finding points where the derivative match the average rate of over the rate of change over an interval. And it is widely used in numerical analysis and approximation method. And then the last application is supporting theorems. So mean value theorem serve as a fundamental concept for the other theorem in calculus. So for example, the first derivative test and second derivative test. And it used to analyze function behavior and concavity, which provide insight into critical points. That's all for me. Thank you.
Good day to Dr. Ang. My name is YIING. Now I would like to talk about the problem statement. In this project, the aim is to answer the following questions which are closely related to mean value theorem. First is how to prove attracting and repelling fixed point theorem, which is theorem 5 in chapter 4. Second is how to prove corollary 2 in chapter 3. And finally is how to solve the discrete dynamical system using the corollary and also theorem. Now we have to prove the attracting and repelling fixed point theorem. Consider a discrete dynamical system governed by the difference equation xn plus 1 equal to fxn, where s0 is element of I, where I is subset of R, and function f from I to I. Let P be element of fixed f such that f is a continuous on I and continuously differentiable on an open bound interval J subset of I containing P. If modulus of f prime P is less than 1, then P is an attracting fixed point. We call it as SING. If f prime P modulus is greater than 1, then P is repelling fixed point and we can call it as source. Here is the proof. To prove the above theorem, let us define the mean value theorem. Mean value theorem as here. Let f be R. If f is continuous in the closed interval AB and differentiable on the open interval AB, then there exists at least one point, we call it C, is subset of open bound AB, such that f prime C equal to fb minus fa divided by b minus a.
Hello everyone, my name is Gong Zijing and I would like to continue explain how to prove the attracting and repelling fixed point theorem. For the first part, which is attracting fixed point theorem, we suppose that the absolute value of f prime p less than 1. By the mean value theorem, we know that for any x inside the real number, there exists a point C in between p to x such that fx minus fp equals to f prime c x minus p. And we know that since p is a fixed point of f and p will equals to p, hence fx minus p equals to f prime c x minus p. And since we assume f prime p less than 1, we can choose any k in between 0 to 1 with f prime p less than k less than 1. Furthermore, since f is continuous as p, there exists a delta such that if c is inside the interval, then f prime c will less than k. Combining all of this information, we will get fx minus p less than k x minus p. Similarly, if we compute for f square x minus p, we will get less than k square x minus p. And we repeat the same argument until n. We can deduce that for all n, f n x minus p will less than k to the power of n x minus p. Since we know that k is less than 1, hence the limit of kn when n approaches to infinity will be equals to 0. And by this, we can conclude that f and x will approach to p, and p is an attracting fixed point. For part 2, which is repelling fixed point theorem, the proof is very similar to the attracting fixed point theorem, which is first we use the mean value theorem. And since in this case, we assume that f prime p more than 1, hence we can choose any k inside 0 to 1 with f prime p more than k more than 1. Furthermore, since f is continuous at p, there exists a delta more than 0 such that if c is inside the interval, then f prime c will be more than k. Combining all of this information, we will get fx minus p more than kx minus p. Similarly, if we continue for f square x minus p, we will get more than k square x minus p. And we repeat the same argument until n, we will get f and x minus p will more than k to the power of n x minus p. However, in this case, since k is more than 1, hence when n approaches to infinity, the limit kn will approach to infinity too. Hence, we can conclude that f and x approach to infinity, and p is a repelling fixed point.
So this is the corollary 2 in chapter 3. So let f and f prime are both continuous on closed interval AB with fab is the proper subset of AB and modulus f prime x is less than 1 for any x in the closed interval AB. Then f has exactly one fixed point P belongs to the closed interval AB. Moreover, period point of f is equal to P and stable set of P is the closed interval AB. So this is the proof. Since we are given f and f are continuous and FAB is a subset of AB, then by mean value theorem, there exists a constant C belongs to XY and which is a subset of interval AB such that f prime C is equal to Fy minus Fx divided by y minus x. Then we're taking the modulus on both sides. Okay, then we are given that modulus f prime x is less than 1 for any x belongs to closed interval AB. So there must exist a constant alpha belongs to 0 to 1, or we say alpha less than 1 such that f prime C will less or equal than alpha and less than 1. Therefore, modulus Fy minus Fx will be less or equal than alpha times modulus y minus mod x. Then suppose we have a matrix D is given that dxy is equals to modulus y minus x. So for any xyz belongs to closed interval AB, we can show that dxy greater than 0, dxy equals to 0 if and only if x equals to y, dxy equal to dyx. Dxz equal it will be less or equal than dyz plus dxy. Therefore, x equals to closed interval AB with matrix D is a matrix space. Then, since real number is a complete matrix space and x equals to a closed interval AB is a subset of real number, therefore x is also a complete matrix space. Now we have three information. First one, the function of x mapping it become the subset of x. Then x is a non-empty complete matrix space. And thirdly, modulus Fy minus Fx will be less or equal than alpha times modulus y minus x for alpha less than 1. So by the metric definition, we can define it become dfx Fy will be less or equal than alpha dxy. So by Barnard contraction mapping this principle, there exists a unit fixed point P which does not move or lay on the mapping. That is, the period point of f is equal to P. Then by definition of stable set, the stable set of P is equals to the set of x in A, B such that Fkx is equal to P as k tends to infinity. That is, the stable set is the closed interval AB. This completes the proof.
Hi everyone, I am Desmond CHING. Today I would like to present the part of the example and the solution of this assignment. We suppose the functions is equal to the s cubed minus s over the 3. Then to determine the fixed point, we need to find that the values of the s for the functions is equal to the s. Then we can see that the s cubed minus the s over the 3 is equal to the s. Then we simplify it, we can find that the fixed point of the function is equal to the -2, 0, and 2. Then we take the first derivative of the function is equal to the s squared minus 1 over 3 to determine whether the fixed point are repairing or attracting. Then we substitute all the fixed point into the first derivative of the functions. Then we can get that the s equal to the -2 and the 2 are repairing fixed point, since their modulus of the first derivative of the functions are greater than 1. Then we can see that the fixed point 0 is attracting, since the modulus of the first derivative of the function is less than 1. In the coordinate diagram, we can see that if the points towards the -2 and the 2's are repairing away from the -2 and the 2, we can say that the fixed point -2 and 2 are repairing. Then if the fixed points, if the points towards the 0's go towards the 0 points, we can say that the fixed point 0 is attracting. In conclusion, the theorems and the corollaries are successfully proven by the mean values theorems. An example is shown to find the stability of the fixed point in the discrete dynamic system. Then lastly, the coordinate diagram are plotted to show the stability of each fixed point. Then that's all our presentation. Thank you.